Okay, so this video is just going to be an extension of problem 3, but we're going to do it in spherical instead of cylindrical. And basically the purpose of this video is to explain the concept of spherical, uh, of the spherical coordinate system and converting between Cartesian and spherical for the purpose of triple integrals. Um, and I figured this would just be a good example to do that with. And also because this is an example that he did in class on Thursday, because I asked him to on accident. The first thing you're gonna want to do, and like I said before with cylindrical, when you're converting between systems, you're not just like jumping right into the integral, you want to graph the bounds. So we're gonna graph the z because the z is the one that has the most variables in it. So we're gonna graph that. That's the three-dimensional one. So let me actually zoom in. This is gonna be the z-axis. This is gonna be the y-axis. This is gonna be the x-axis. So, well, that axis is kind of small, but that's fine. So now, just gonna label them z, y, x. And if you remember from the cylindrical example, the z is just going to be a sphere. The bottom bound is the bottom of the sphere, the negative half of the sphere, and the top bound is 0, so it's just going to be the bottom half of the sphere, which we can figure out by looking at the bottom bound, going z equals negative square root 1 minus y squared minus x squared, and then going, okay, so z squared equals 1 minus y squared minus x squared, which means that z squared plus y squared plus x squared equals 1. And then we know it's a negative half because it's negative here, so it's going to be below the z-axis. So, or on the negative side of the z-axis, I should say. So let's draw the sphere. Let's just draw the whole sphere, and then we'll shade in the negative part. And our region bounded on the bottom by the negative half of the sphere, bounded on the top by z equals 0. So do this. Just go bottom to top. And now that we have the three-dimensional region drawn, it's time to talk about what the spherical coordinate system is. So the spherical coordinate system is, if you remember, is put in terms of rho, which is the distance from the origin of the xyz axis, theta, which is the horizontal rotation around the origin of the x and y plane, and phi, or phi, which is the vertical rotation around the z-axis. So, basically, we need to put this Cartesian triple integral in terms of rho, theta, and phi. I also don't know if the standard notation is actually in this order. I just kind of figured and drew it like that. It doesn't really matter. You're not doing it like that. It doesn't matter. All right. So the first thing what we're gonna do is we're gonna find theta. So to find theta, you need to map out the region on the xy plane. So the first step of mapping out the region is taking the three-dimensional drawing that we drew, that we were able to get from the z-bound because it has the two variables in it, which makes it three-dimensional. we take the three-dimensional region we drew and we map it onto the xy plane, and we flatten it, make it two-dimensional. So if you remember, flattening this, because this is a sphere with a radius of 1, we flatten it and we just get the unit circle, which is a circle centered around the origin of x and y with a radius of 1. So and then that's a horrible circle, but whatever. The next thing what we have to do to get theta is we just have to know how much of this circle is actually used in the total and the whole bound of the integral. How do we figure that out? Well, if you remember, for cylindrical, what we did is to figure out how much of the total circle is used, we look at the y and the x bounds, because now it's mapped on the y and the x. So first, the y bounds, or whichever bound has the single variable in it, which makes it two-dimensional, which is almost always going to be the y one. We have bounded on the bottom by negative 1 minus x squared, which, if you remember, is just going to be the negative half of that circle, because we can convert it into y squared equals 1 minus x squared by squaring both sides, and then we get y squared plus x squared equals 1, which is just this circle, and since it's on the bottom, it's negative half. It's negative. That means it's gonna be the negative half of the circle. And then the top bound, the upper bound, is gonna be at the positive half of the circle, because you can do the same thing where you get a circle with a radius of 1 centered around the origin by squaring both sides and moving the x over. And this one's positive, so we know it's going to be the top half of the circle. So it's bounded at the bottom by the negative half of the circle, and at the top by the positive half. So we're using the whole circle on the y-axis, and then what are we using on the x-axis? Well, the x-axis starts at x equals negative 1, which is right here at this end of the circle, and it ends at x equals 1, which is right here at this end of the circle. And so what we can do is we know that it goes through the whole x-axis of the circle, basically. And then we know the y-bound is just the whole circle. So that means that we know we're using the whole circle. So now that we understand that, and I can draw the x like this too, just so you can see it from the left to the right. But, now it's a little ugly, so let's get rid of that. So now what we can do is we understand the whole circle is being used. Theta is essentially, you find it by seeing you remember theta is just the rotation along, through, it's the horizontal rotation, which is like the rotation through the xy axis. So it just basically is saying how many degrees through the xy axis are being used. Since the entire unit circle through every quadrant is being used, it's like this. And it's going to go from 0 to 2 pi, which is the same as the cylindrical. Because remember, theta is the same either way. Theta is the same conceptually for both cylindrical and spherical. So that means that theta is going to be from 0 to 2 pi. And that'll be our theta bounds. Okay, so now this is probably the hardest part of spherical is phi. Or at least the hardest part for me to understand, because I think with theta, it's like you have to understand it first, because you have to know it to do cylindrical, and to know how theta works to do the other one in polar in 2 dimensions. But the next thing is phi, which is exclusive to cylindrical. And the way phi works is essentially the vertical rotation around the z-axis. So I'm gonna draw the invisible z-axis that you can't technically be able to see. Basically, it's saying, now I can't get it. It's saying how much is being, how many degrees are being used from positive z to negative z. Okay, and so because of that, the minimum like theta phi could be is 0, because it then 0 would basically just mean like phi equals 0 is right here. It's on the positive z-axis. If you have a point, or if you have like a line here, this would be where phi equals 0 is. It's like the same thing as like theta equals 0 along the x-axis, or along the positive x-axis. And then the greatest number, unlike theta, the greatest number that phi can be is pi. Phi cannot be any greater than pi, because if you drew an angle like this that starts at positive z and goes all the way down to negative z, that's only going down pi. This is half of a circle, right? Whereas with theta, you're going around the whole 2 axes, so you're going 2 pi, a whole circle. Phi just revolves around the z-axis, so it starts on the positive z-axis and it ends in the negative z-axis, and if it goes through the whole thing, that means it's going from 0 to pi. Now if you remember, phi is not starting on the positive z-axis, right? Because the z is bounded from 0 to the negative half of the sphere, which means that it does go to this negative half. It intersects the negative half of the z-axis here, or it intersects the negative z-axis here, but it never actually touches the positive z-axis. It's basically, it starts at this origin point here. So it's going from here basically to here, if that makes sense. Or, if I want to do it, it's from here to here. So instead of using this full line, this full axis, it's just using the bottom half of the z-axis. And so since it's only using that bottom half, that means that this angle here, phi, is just going to be 90 degrees, which is just pi over 2. So what does that mean? Well, since phi is in reference, since phi, we're trying to find bounds. Phi is, in reference to the z-axis. Positive z starts at phi equals 0. If you go from phi equals 0 to just z equals 0 here, so positive z to z equals 0 here, and you're just using this top half, you would be going from phi equals 0 to phi equals pi over 2, and that would be the bounds. But that's not what we're doing here, right? We're using the bottom half. We're not using the top half. So instead of starting at phi equals 0, we're actually starting here at phi equals pi over 2, which is where z equals 0. The middle of the center between phi equals 0 and phi equals pi is pi over 2, right? So we're starting here at z equals 0. And so that means that the lower bound of phi is going to be pi over 2. And then it's ending right here, right, on the negative z-axis, because it's going from z equals 0 to the negative half of the sphere on the z-axis, which means that it's starting here and ending here. So that's starting from phi equals pi over 2 and ending where z is negative, on the negative z-axis. And on the negative z-axis, if you remember, it's phi equals pi. So that means that the bounds for phi are going to be pi over 2 to pi. And so with that information, we now have the bounds of theta and the bounds of phi. And that leaves us with just rho, which is probably the easiest one generally, or at least usually is going to be the easiest one, though I could imagine it probably could be a little bit more complicated with more complicated shapes, and I think on Sunday we'll probably have better practice with more complicated shapes, like some of the ones we did in class, and that way we'll be more ready for the exam. But rho is essentially just it's probably the easiest one. It's just the distance from the origin, right? So rho is basically like the radius, but in 3-dimensional. So it's just the same thing as r essentially, but in 3D instead of 2D. So like when you're converting to cylindrical, you have to map on the XY plane to get r, because r is like 2-dimensional. It's the radius of the circle is being used, but in this instance, it's 3-dimensional, and it's just basically like how far from the origin are you going. And like r, the bounds for rho are almost always going to start at 0, and then we just need to, and then you just put the radius of the sphere for the upper bound. So lower bound is going to be almost always going to be 0 because it's starting at the origin, and then it's going to where where the sphere ends, like the distance from the origin. And because the radius of the sphere we already know is 1, rho is going to go from 0 to 1. So now the bounds for theta we have are 0 to 2 pi, because we're using this whole circle in 2 dimensions, which means that the horizontal rotation around the xy axis is 360 degrees, because we're using the whole circle, which is 2 pi, and it starts at 0. And then we have the phi bounds, that's just pi over 2 to pi, because we know that the vertical rotation is starting here at z equals 0, because it never goes to the positive, and it's the upper bound is at 0, and it's ending at the negative z, because it's the lower bound of z is the negative half of this sphere here. So it's starting at phi equals pi over 2, which is where z equals 0, and ending at phi equals pi, which is the negative z, and then rho is just starting at 0, because if you're drawing a line that's showing the distance from the origin, you start at the origin, you start at 0, and it's going to the radius or the end of the sphere, which is just the radius of the sphere, which is 1. So now we have our bounds, and now all we have to do is convert this integrand here to spherical instead of Cartesian. So first, let's just write our bounds down. I'll write rho first. So, or not rho, sorry. We'll write rho first. So rho is starting at 0, ending at 1, and then I'll go with phi is starting at pi over 2, ending at pi, and theta is starting at 0, ending at 2 pi, and we have and then we just have the integrand. If you remember, when we were converting to cylindrical, we also had to translate the z bounds into cylindrical. You don't have to do that here because cylindrical keeps the z bounds, so we had to translate it into cylindrical because it had the x and the y. Or the cylindrical keeps z in it, right? So z is a part of the cylindrical system, whereas spherical, we got rid of x, y, and z, so there's no translating the bounds here, really. It's just drawing it and figuring out what rho, phi, and theta are. So, now what you're going to want to do is you're going to want to write... we just have to plug stuff into the formulas. So if this is like, you're gonna have to memorize this. Same thing with cylindrical, where the x equals r cosine theta and y equals r sine theta. For spherical, we have different formulas. So we have x equals rho cosine theta. Actually, let me get the formulas out just in case I miss them, because I don't want to screw this up. Okay, I was gonna get them right, although my notes actually had them wrong, so I panicked for a second. Okay, so x is rho cosine theta times sine phi. The way I remember this is, generally speaking, cosine is just associated with x. And then so y is going to be rho sine theta times sine phi. And like, so like the way I remember these, right, is they both have the term sine phi in them, and or they both have rho times sine phi in them, and then so you just have like the x as a cosine theta and the y as a sine theta. And for me, it's like I remember it because the rho sine phi is just constant. You just have to remember that, and then you add the cosine theta and the sine theta because it's like, well, then where does theta go? And then you know, okay, theta is gonna go in here for the x, and then there's going to be a cosine for x and sine for y because that's just how it is. And then z is going to be rho cosine phi. The way I remember this one is just they all have a rho, so the rho is going to be there. And then cosine phi, I really the only reason I remember this one is because cosine cosine phi doesn't appear in any of these ones. It's like the only combination of angle and trig function that doesn't appear in these two. And so I'm like, well, cosine phi is the only combination of like for example, like cosine theta is in here, but there's no cosine phi anywhere. And then like sine phi is in these, but there's no cosine phi. And then cosine phi is for the z. That's the only way I remember. Is this one has just the only instance of that. And like sine theta and sine phi are in there, and cosine theta is in there. But yeah, and then rho is just in all three. I don't know if that was a really good explanation for memorizing it, but that's just how my brain works. Yeah, I'm gonna make sure I wrote this down correctly again. Okay, yes, I did. Just had to make sure one last time. Okay, so we have these formulas. So now we just have to convert the x, y, and z by plugging them into the formulas. So zx squared is going to be, so z is, let me just zoom out so I can have it visible. There we go. So we have z, so rho cosine, let me do that, cosine phi times x squared, which is just going to be this rho cosine theta sine phi squared, and then plus, I actually need to write smaller so that I can fit this, z times rho cosine phi times rho, and then the y squared is just going to be rho sine theta sine phi squared. And then pretend like I wrote, actually so yeah, there's one more formula. We need to put dz dy dx in terms of spherical, in terms of, you know, the d, what was it? Why did I write it in this order? Yeah, d theta, d phi, d rho. We need to be able to convert that, and there's a formula for that. I actually just don't remember it, so I'm gonna have to look it up. Okay, I have them now. So this is just gonna become rho squared. No. Rho squared times sine phi, and then it's just gonna be d, this is theta, d theta, d phi, d rho. Obviously the order you have the variables in doesn't matter, it just depends on the order you're integrating in. And also just because that's how multiplication works, you can do it in any order. And essentially, the the way I memorized this one, which obviously I didn't do a very good job considering I had to look this one up, but the way I memorized this one is sine phi shows up in all of these except for the z. If you're forgetting a formula, sine phi is probably in it. is the way I kind of think about it. Except sometimes it's just not. So the one time it's not, but whatever. And then the rho. Just remember this is rho squared. You just have to. Basically, what I'm saying is just memorize it. Don't use a trick. I don't even know. There's no trick. just do it. My advice to you is to look at it last minute before the exam, or get so comfortable using it now that you actually already know it before the exam. That's that. I'll probably do both those things because I'll probably get it mixed up with something at some point. But anyway, pretend like I wrote this. This is so ugly. This is so. Let me just. Uh-huh. Right. Okay. And then I can just times rho squared times sine phi times d theta d phi d rho. Okay. Now, what we're gonna do is okay. What we're gonna do is we're gonna simplify what's in the parentheses here, and then we can distribute this rho squared sine phi after the fact. But first, let's just simplify what's in the parentheses. Most of the time, when you're converting to spherical and cylindrical, you're going to do the trick with the cosine squared plus sine squared equals 1. There are other trig identities he told us to memorize. I think I'm just going to raw dog it, to be honest. I don't feel like memorizing trig identities other than the secant squared minus tangent squared is 1 and the cosine squared plus sine squared is 1. And I doubt we're going to get the secant tangent one. So I wouldn't worry about it too much. Half angle theorem is probably worth memorizing. I just don't care. So we have rho times cosine phi, which is the z, times rho squared cosine theta squared times sine theta squared plus rho cosine phi times rho squared times sine theta times sine theta squared times sine rho squared times rho squared times sine phi. I think I accidentally said sine rho instead of sine phi, but earlier, but I'm sure you saw it, what I meant. D theta, d phi, d rho. This is horrible. This is so. All right. Now let's simplify it. So let's see. I would combine these rows. I'm doing it very slowly just so you see all the steps, but I'm sure you can already see it. I would combine this row and make it row cubed. I'd combine this row and and make it row cubed. And then I would distribute this row squared to each term, and then both of them would become row to the fifth power. And then you can take that row to the fifth power, take it out, and then you can also take the sine phi squared out, and it becomes row to the fifth power times sine phi squared. And then in the inside of the parentheses would be cosine theta squared. Also, you have to take the cosine out. Okay, we're gonna write it down. So first of all, let's just combine the rows, and then we can distribute the row squared after that. So we'll do this integral, and this is the row integral, and then the theta integral, and then no, this is the phi integral. This is the theta integral, and then this is oh yeah, right. So then we're combining these two rows here. It's all in this term, so this is gonna become row cubed cosine phi times cosine. And if you remember that these cosine phi's are from the z. Cosine squared theta times sine squared theta. And then plus wait. This is not supposed to be. Why does it say theta? Who did this to me? This is supposed to be phi. This is supposed to be sine phi theta. I am so sad about this. I'm sine phi theta squared. Sine phi squared. Yeah? Okay. Plus and then we're in another row cubed. We're combining these two rows again. It's the same thing, but there's a cosine theta in it instead of sine theta. Wait, no. It's the same thing, but there's a sine theta instead of a cosine theta. Okay. Sine phi times cosine. No. What? Row cubed. It's late. Okay, I had to work. Row cubed times cosine phi times sine theta squared times sine phi squared, and then close parentheses, and then row squared times sine phi, and then we have d theta d phi d rho. Okay. We're gonna distribute this rho squared sine phi to each term now, okay? I'm not sure that, yeah, we'll just do it. So let's do that. This is gonna be from 1 to 0, and that's gonna be the rho integral. This is gonna be theta in this is the phi integral actually, and this is the theta integral. And then we distribute rho squared times sine phi, so that's gonna be so each term, and now I can't write because okay, don't worry about it. We're distributing this to this term and to this term, so rho cubed times rho squared is just going to be rho to the fifth. And then this sine phi is just going to go to this sine squared phi. Sine squared phi times sine phi is just going to be sine cubed phi. So let me write down the rest of the terms first. Cosine phi cosine squared theta, and then sine cubed phi plus, and then it's the same thing, rho cubed times rho squared is rho to the fifth times cosine phi times sine squared theta times sine cubed phi. Okay. Then we'll do d theta d phi d rho. Okay. Now the things are combined. We're gonna uncombine them so that we can get cosine squared theta plus sine squared theta in there, and then make that a 1. And then we're gonna do some other things probably. I don't really remember. It'll probably be awesome though. So sit tight. Hang on. This is a lot longer when I'm trying to write out every step and I'm doing it with a mouse. Because I was like, problem is a lot longer than I remember it being. And that's just because I'm writing it with a mouse and I'm writing every step, whereas when I did it on paper, it's faster to write on paper, and I didn't write every step out. So right. So cosine phi cosine squared theta. Right. Okay, sorry. I'm going to take out the phi to the fifth, and I'm going to take out the cosine phi, and I'm going to take out the sine cubed phi, so that I can get cosine squared plus sine squared. And also because those are all like terms, and that's how distributive property works. I have to write it out on another thing. So let's do, well, let me zoom in a little bit. Okay. So we have the what is this? Right, okay. This is the rho integral, and then we have the phi integral, which is pi over 2 to pi, and then we have the theta integral, which is 0 to pi over 2. I don't know why hang on. Don't even worry about it. Don't even worry about it. You did not see that. Then we have the theta integral, which is from 0 to 2 pi. I actually need to go back and check that I did that right. Alright, yeah. And then we're going to take out rho to the fifth. We're going to take out cosine phi, because that's in both terms. And we're going to take out sine cubed of theta. No, phi. Of sine cubed of phi. Or sine phi cubed, because that's also in both terms. And that's going to leave us with cosine squared plus sine squared in parentheses, which is 1. So we have rho to the fifth power times cosine phi times sine cubed phi times cosine squared theta plus sine squared theta, and then we have d theta, d phi, d rho. Okay, cosine squared plus sine squared is 1, which is just going to leave us with an integrand of phi to the 5th power times cosine of phi times sine cubed of phi. So that's going to be from 1 to 0, and from pi to pi over 2. This is the phi integral, and then this is the theta integral, and this is our integrand. So rho to the 5th times cosine phi times sine cubed of phi. No, don't do that. D theta d why am I writing up? D phi d rho. Okay. Now, we're integrating in terms of theta first. If you notice, we got rid of all the thetas. From what I remember, you can really integrate, and you can integrate in whatever order for the sphere for this example. It doesn't really matter. There's not really a better one. It's all gonna kind of work out either way. So I did it arbitrarily, just so you know, in case you thought I didn't. But yeah, all these are constant because we're integrating in terms of theta. Theta does not exist anymore. This is a phi, this is a phi, this is a rho. So that means that the integral of this in terms of theta is just going to be this times theta, right? Because there's no theta. So, and that's how that works. We could move this to their respective integrals. I don't feel like doing that, so I'm not going to until I find that it is more convenient to do that, which I don't currently feel that way about it. So cosine phi sine cubed phi, and then from 2 pi to 0 d phi d rho. Alright, and then we plug 2 pi in. We're just going to get 2 pi times this, and then we subtract, plug 0 in. It's just going to be 0 times this, so that's just going to be minus 0. So that's just going to leave us with the 2 pi one. So it's just going to be 2 pi times rho to the 5th times cosine of phi times sine of phi cubed minus 0. We're not going to write the 0. 1 0, and that's the rho integral, and this is the other one. Actually, I know I said I'm gonna move the rho to its integral just so it's not. Well, actually no. We'll wait. We'll wait to do that. At some point, I probably will move the rho because it's a little bit in the way. Not really, but I feel that way about it. So 2 pi. Times rho to the 5th times cosine of phi times sine cubed of phi d phi d rho. Okay. Now I'm moving 2 pi because it's just a constant number. I'm moving it to the front here. So that's going to be 2 pi. And I'm going to move the rho to the 5th with its integral because I don't feel like having it in my theta integral. Not that you have to necessarily. You don't normally have to when you're moving a constant out, but it makes it more legible for me. And that's going to leave us with, cosine phi sine cubed phi d phi d rho. Okay, this is a U sub problem. Sometimes you'll see like multiplication and you might think, oh well, it must be integration by parts because there's two terms being multiplied by each other. But this is a U sub problem. Whenever you're about to do integration by parts, it's definitely good to make sure that there's not just like something you can set U to real quick and make it so that one term is U and the other term is du. In this instance, that is exactly what you can do, because you can just make U equals nope sine phi. And a good way to remember this, like if this was like not something that you could necessarily recognize, if you start writing this as this instead, it becomes more apparent that sine phi is going to be u, right? Because you see that it's inside of the function of the cubed here. Where you write it like this is like the more convenient, less like you don't have to write the parentheses way to write it. But if it's like you weren't able to recognize that sine phi is the u, then it's definitely worthwhile, at least for a bit, to start writing like trig functions that are set to a exponent in parentheses and just have it set to the whole thing, because it's much easier to recognize something like this, like, oh, this is going to be the u here. So now we know u is sine phi, and that means that du is going to be cosine phi d phi. And that's going to be, so that means that the whole thing's going to be 2 pi. Actually, let me fix the bounds real quick. That's my bad. All right. So u is sine phi, which means that we're plugging the bounds in. So phi equals pi implies that u equals sine of pi. Sine of pi is just going to be 0. And then phi equals pi over 2 implies u is going to be sine of pi over 2, which is just going to be 1, which means that the bounds for u are going to be lower bound 1, upper bound 0, right? Because you plug pi in, you got 0, you plug pi over 2, and you got 1. So make sure you don't swap those just because 1 is greater than 0. Just make sure you keep that in mind when you're doing a u sub, to make sure that you're putting them in the correct order, even if it looks weird. And then so lower bound 1, upper bound 0, and then we have cosine phi d phi is du, right? So this and this become du, and then what we're left with is sine phi is u, and this is sine phi cubed, so it's just going to become u cubed. So we have u cubed du, and then d rho. And now that we have the u sub done, we can just integrate the u. So you have 2 pi times the rho integral, rho to the 5th power, times integral of u cubed is just going to be 1/4 u to the 4th. And then from 1 to 0, it's going to be plug in 0, you get 0. So 2 pi and then 1/4 times. So plug in 0, you get 1/4 times 0 to the 4th power. 0 to the 4th power is 0. 1/4 times 0 is 0. So we have 0 minus, let me plug 1 in. 1 to the 4th power is 1. So that's just going to be 1/4. So minus 1/4. Oh, wait. Sorry. No. 1/4 times 0 is 0. Minus 1/4 times 1. It's going to be negative 1/4. And then D rho. You could have done it the way I was writing it before, but I don't want to. And then the rho integral. And then times negative 1/4 d rho. Now I'm gonna move this negative 1/4 on the outside because it's just a constant number, and that way we're just left with rho to the 5th in the inside of the rho integral. So we have 2 pi. We have negative 2 pi over 4, which is just gonna be negative pi over 2, which I'll simplify in the next step. Rho to the 5th power d rho. And then the integral of rho to the 5th power is going to be 1/6 rho to the 6th. So we're going to do negative 2 pi over 4 is going to be negative pi. Okay, well. Negative pi over 2 times 1/6 rho to the 6th from 1 to 0. This is lower bound 0, upper bound 1 this time. So plug in 1. You get 1/6 because 1 to the 6th is 1. And 1/6 times 1 is 1/6. So negative pi over 2 times, and then we got 1/6 minus 0. That's going to be negative pi over 2 times 1/6. And then that's going to be negative pi over 12. And that, if you remember, is the same answer we got for when we did it in cylindrical, which means that we're right. Hooray! Alright, that's how you do it in spherical. I'm not sure if it's really worth watching me do the actual integral for this, but I do think that I did a pretty good job explaining, or actually I don't know if I did a good job, we'll find out. I think that it was pretty, I think the first part of this video is pretty good, so I'll upload it. Alright, let me know if there's anything else I can explain, and then I'll see you Sunday and I'll explain that stuff more there.